Hello and welcome all the TYBSc physics students, those who are preparing for the Savitribai Phule Pune University semester 1 examination, TYBSc semester 1 examination for the paper Atomic and Molecular Physics. Today we are going to discuss some important concept based MCQs, multiple choice questions on the chapter number 7, that is Raman Spectroscopy. And as you know, we have already seen 5 different chapters and their MCQs in earlier videos. I hope all these videos might be useful for you all while preparing for this university examination. In this series, let's go for today one of the important chapter and conceptual one, that is the Raman Spectroscopy. As we know, this particular spectroscopy lies in the range that is far infrared or infrared radiations, or on the boundary of visible and infrared radiations, and that's why it is bit different than this X-ray spectroscopy as well as spectra for 1 valence electron system, spectra for 2 valence electron system, as well as hydrogen spectrum. This entire phenomenon here is the molecular phenomenon. That means a substance, transparent substance, its molecules, they get excited, and from excitation state they go down to this normal state or ground state, and in this particular transition sometimes it is possible because of this vibrational energy states, these molecules may be in different levels of vibrational states, and therefore some different radiations are radiated other than what is absorbed or what is radiation that is absorbed by these molecules. So this particular concept is basically different than whatever we have discussed in earlier chapters. So where this electronic transitions, electron gets transition from electron from higher to lower orbit or lower to higher orbit. According to that, we have this either emission spectra or absorption spectra and like these things. Here in this case, phenomenon involved is bit different. The molecules itself, they rise and fall in the different vibrational levels, and that gives rise to the spectrum which is called as a Raman spectroscopy. So in the discussion, we are going to discuss all these topics, all these particular concepts one by one as follows. So let's go for this question number 1. Very simple, easy and conceptual question. When a monochromatic optical radiation passes through pure transparent substance like air or water and like this, it undergoes a scattering in addition to absorption and transmission. This is known as, so straightforward, this is known as Raman effect. It is not Auger effect, because Auger effect is basically in the X-ray spectra whenever more than 1 electrons are dislocated from the internal structure or internal shells of this particular atom, and when these particular vacancies are filled by outer shell electrons, this concept or this particular transition takes place, that is called as Auger transitions, or the effect is called as Auger effect. Rayleigh scattering, that is the normal scattering with which or because of which we see the light or the sky around us. The sky which we see is usually blue, and this is a regular normal scattering where light radiations get scattered, or the strength of the scattering is directly proportional to 4th power of the radiation. So here this is in the Rayleigh scattering, this strength of scattering, this is directly proportional to 4th power of the frequency of the radiation. This is a normal scattering, and because of that we see that there are several different types of radiations, blue, green, red, yellow, etc. Out of that, this blue color gets more scattered as compared to red and yellow and all other colors, and therefore sky appears blue. Okay, sky appears blue, that is your Rayleigh scattering, and this particular scattering is one of the dominant scattering where this particular air molecules gets excited as well as get de-excited, and this entire process is called as this Rayleigh scattering. So Auger effect is from X-rays. Then this Raman effect is that where we usually find there are 3 different lines are observed, and these lines are as shown. So this line is exactly having the frequency which is given by this Rayleigh scattering. So this is called as Rayleigh's line. Okay, Rayleigh's line, this scattering line is, and below that there is some line having some frequency delta nu, and this particular line is called as Stokes line. That means on both sides of this Rayleigh's lines there is find one line below the frequency and one above this frequency, which is given by nu plus delta nu. This is Raman shift, and this particular line is called as anti-Stokes line. So these are the two different types of radiations emitted at the same time along with this Rayleigh's radiation or Rayleigh's line, and this particular effect is called as the Raman effect or Raman scattering. Note that here this scattering is this type of relationship is not valid there, but here we are having some different relationship. The intensity of this particular scattering is much less as compared to intensity of this Rayleigh scattering, as well as other types of scatterings and so on. So actually we have designed certain questions based upon this scattering strength and all that. So try to understand this Raman scattering is totally different than Rayleigh scattering. So Rayleigh scattering is normal ordinary scattering, whereas Raman scattering is different. It is because of the different types of vibrational levels of the molecules. This type of radiations are emitted along with this original radiations or normal radiations, and this is how this particular effect is called as Raman effect. So this is what a introductory thing. Then second, as I said, Raman scattering is weak and is about -% of the radiation or less than -% of the scattering, Rayleigh scattering. So Rayleigh scattering is very dominant part in the molecular scattering or the scattering of light in the air or whatever transparent medium we go for. So in this case, this is one of the very weaker part, and that shows you it is just 0.01% of the incident radiation, and it is just 1% of the Rayleigh's radiation or Rayleigh's scattering. That means if 100 units of light is incident on some this is from transparent material, and if this light is incident here from this side, this is medium here I am taking, and here almost 99% scattering is observed to be of this Rayleigh scattering. Okay, and whereas just 1% or less than that, this particular scattering is found to be 1% of this is found to be this Raman scattering. And this Raman scattering, if we calculate its proportion to this incident radiations or the total energy incident, that is 100 units you have taken here, this part is very small, that is 0.01% of this much radiation undergoes this process of Raman scattering. Almost 99.99% radiation undergoes this particular Rayleigh scattering, and as compared to this is just 1% or less than that. That's why Raman scattering is one of the very weak phenomenon. It requires large another type of heavy resolution type of instrument to identify this type of scattering, but that gives you one of the very important, many other important properties of substances or molecules. Transparent substances can be introduced or can be studied with the help of this Raman scattering. So this is a phenomenon which is different than this Rayleigh scattering, and that has many applications, many applications, over which also we are going to see some questions in later on. Then question 3. In Raman spectroscopy deals with the measurement of intensity of scattering radiation as a function of, naturally, velocity of light doesn't play a role here, energy of the radiation also doesn't play here, it is immaterial of that, and it is a proportional to the wavelength. So depending upon the wavelength, so as a function, so scattering radiation is a function of wavelength. As wavelength of this incident radiation changes, the amount of scattering changes, and that's why scattering radiation is a function of the wavelength. Density of medium doesn't play any role, so that is directly related to this Rayleigh scattering. So Rayleigh scattering and density of the medium, that has some relationship, and therefore this is not applicable here in Raman scattering. So in Raman scattering, wavelength of the radiation, that is what of which what is going to be scattered. So to what extent it is going to be under Raman scattering, that depends upon this wavelengths. Therefore, question number 3, in Raman spectroscopy or Raman spectroscopy deals with the measurement of intensity of scattering radiation as a function of wavelength of the incident radiation. It is not dependent upon any either energy nor density of the medium, nor it depends upon the velocity of light. It depends only upon the wavelength of the incident radiation. Then question number 4. The lines in the Raman scattering are frequently arranged on both sides of the Rayleigh's line. So as we have drawn this diagram earlier, this in between or central line is called as Rayleigh's lines, and the line here on the right hand side and line here on the left hand side, which we have obtained here, this is nu is equal to nu 0, the frequency. Here nu is equal to nu 0 minus some delta nu, some frequency is less here, and on that side, right hand side, this is nu 0 plus delta nu, some additional frequency added there. So in the frequency range, as we go on increasing this frequency, the lines which are observed on the left hand side of this Rayleigh's line, these are called as Stokes lines. Okay, and the lines which are observed on the right hand side of this Rayleigh's line, these are called as anti-Stokes lines. So many times there can be several questions on this particular Stokes lines, anti-Stokes lines, then their frequencies relations, what is the frequency of the Stokes line, what is the frequency of this anti-Stokes line, etc. These questions can be asked over this particular simple diagram. And remember, both of these Stokes and anti-Stokes lines, these are symmetrically spaced. That means it is not, picture is not like this. This is central line, then this is Stokes line, and this is anti-Stokes line. This picture is not there. The picture shows here this delta nu observed in this case and delta nu observed in this case, they are equal, and that's why this is called as symmetrical. So we get symmetrically spaced Stokes lines and anti-Stokes lines from this Rayleigh's line. Therefore, the lines in the Raman scattering are frequently arranged, not frequently, commonly, generally arranged symmetrically on both sides of the Rayleigh's line. So question number 4, correct option is B. Okay, next we'll go further. The line of frequency less than the Rayleigh's line is, okay, just now we have discussed, it is called as a Stokes line. So on the frequency diagram, on the frequency range, this is the frequency if it is increasing here, this is Rayleigh's line, this is Stokes line, and this is the frequency, or this is the line which is having which is called as this anti-Stokes line. So this is what the difference, and therefore before, this is Raman's line, okay, this is Raman Stokes line, and this is Raman anti-Stokes line. Okay, try to understand this, anti-Stokes lines. So Raman Stokes line and Stokes lines and Raman anti-Stokes lines. So Raman Stokes lines has some less frequency, whereas Raman's anti-Stokes lines has some more frequency as compared to Rayleigh's lines or the original wavelength or original radiation, and that's why the question number 5 correct answer is again E, that is Stokes lines. Then question number 6. Now this question is related to the frequency. So what happens whether the frequency increases or decreases, and based upon that, let's see something very interesting fact here. Question number 6. The dash in frequency, either decrease or increase in frequency, giving rise to Stokes lines, and dash in frequency give rise to anti-Stokes lines, depending upon whether the molecule starts in ground state or an excited state. Okay, so that is how we have to draw one more picture again later on. So in this Raman scattering, you might have drawn this picture earlier in your classroom discussion, that is the energy diagram of the spectrum, this Raman spectrum. In this particular, these are the different vibrational levels I am drawing here. This is one vibrational level which we have called term it to be 0, and there is one more level above this. This is vibration level 1. And now when these radiations or these molecules absorb certain radiation, it reaches different energy levels. I am calling these two levels common, and there is some difference here as shown there. Now when we go for this particular radiation or there is absorption, and this is h nu 0, so frequency of this radiation is nu 0, so total energy absorbed is h nu 0. There is a possibility that this is a metastable state, or a molecule doesn't remain in that state for a or longer time. There is a chance this molecule may undergo a transition, and this time it will give you a radiation. This is given to be h nu 0 minus h nu. So naturally difference between these two is h nu. This is vibrational energy difference of the ground state of that particular molecule. Then sometimes it is possible that whatever radiation absorbed here while going this molecule from this zero vibrational state to this excited state, and it comes from this excited state to again zero vibrational state. So whatever h nu 0 was absorbed and h nu 0 was given, and therefore this is a line here. This is what a line which is having h nu 0 minus h nu. This is simply h nu 0. This is your Rayleigh's line. This is the Stokes line, and here also there is one more possibility that the excited state itself is higher than this excited state by difference h nu, and therefore there is a chance this the molecule absorbs it is in ground state, it is in first vibrational state, it absorbs this radiation h nu 0, original radiation incident, and upon it is going on this level, vibrational level n equal to 0, and this time it radiates some more frequency which is given by h nu. Note that this difference is again h nu, and therefore I get another radiation. This is h nu 0 plus this is h nu, and this is what your anti-Stokes line. So anti-Stokes line, okay, and that's once we understand how Stokes lines, how anti-Stokes line, how these Rayleigh's lines appear in this particular molecular scattering or Raman scattering, then it is very easy to understand this. The increase or decrease, now there is a decrease, okay, decrease in the frequency giving rise to Stokes lines. So that's why you have seen here h nu 0 minus h nu. This is a decrease in the frequency, therefore it decrease, and increase in frequency give, and okay, there is increase in frequency, there is plus h nu. Here is the decrease in the frequency, this is minus h nu. Therefore this is decrease and increase. This correct option is here. Question number 6, we'll read it once again. The decrease in the frequency giving rise to Stokes line and increase in the frequency give anti-Stokes line, depending upon whether the molecule starts in ground state or in excited. So where it is start and from where it is start, depending upon that we get Stokes line or anti-Stokes line. Where there is some fall in frequency, there is again some rise in the frequency, and based upon these lines called as Stokes lines or anti-Stokes lines. So remember this simple diagram wherein we have shown two vibrational levels, and this molecule gets excited from this vibrational level to some higher level, and then this energy transitions occur, and because of that radiations are emitted, which are called as Raman radiations or Raman scattering. So Raman scattering, Stokes lines, Raman scattering, anti-Stokes lines, their origin, their energy, etc., that can be understood from this simple diagram what we have drawn here. Now this is again a same thing here. For Rayleigh's lines, the observed frequency nu is equal to nu 0, that is original frequency here, whereas Raman Stokes line has observed its frequency is to be this. Okay, so it is nu is equal to nu 0 minus this vibrational energy, and therefore this is the correct option. Whereas nu is equal to nu 0 plus vibrational, this is for your Rayleigh's line. Sorry, this is not for, this is for the anti-Stokes line. Okay, so this is what the expressions we have already seen, and this is not applicable here. It is plus minus V vibration, this type of lines are not observed, as well as minus plus, this is also not observed there. So either you will get nu is equal to nu 0 or nu is equal to nu 0 minus nu vibration, that is what Stokes lines, and nu is equal to nu 0 plus nu vibration, that is called to be anti-Stokes lines. So Stokes lines, anti-Stokes lines, and Rayleigh's lines, these are the only three possible lines. Other than that, other types of energy or frequency values are not possible, and that is what called as the Raman scattering. Okay, next question number 8. According, this is what earlier we have seen the questions which were based upon the classical theory. Now there is some quantum theory also, the quantum theory of the Raman effect. So according to quantum theory of Raman effect, the collisions is elastic. So this is what the collisions that are occurring here are elastic. There is dash from the photon of molecules and vice versa. Hence a photon is scattered without change in energy and frequency of the photon is the same as the incident photon, or that is what the second line here. Hence a photon is scattered without change in energy and frequency of the photon, which is the same as the incident photon, and that's what This is what a Rayleigh scattering, and the earlier statement is related to Raman effect, and therefore here there are four options given. Option is no transfer of energy, option B is partial transfer of energy, option C is complete transfer of energy, and option D is none of these. Here there is no transfer of energy is applicable because this is applicable for Raleigh's. This is also applicable for Raleigh's scattering. So Rayleigh scattering is a regular molecular scattering where scattering strength is directly proportional to 4th power of the frequency, whereas Raman scattering is totally different than that, and therefore no transfer of energy. So we'll read again once again the statement. According to quantum theory of Raman effect, the collision is elastic. There is, as it is elastic, that means no loss of energy, so no transfer of energy from photon to molecules or molecules to photon. Therefore, in the collision, if the collision is elastic, there is no transfer of energy from the photon to molecule and vice versa. And here this type of scattering observed, which is different than this Rayleigh scattering, and that's why correct option of this question number 8 is A, no transfer of energy. Now question number 9. Again, Stokes lines are dash dash than the anti-Stokes lines, whether they are stronger, whether they are weaker. Okay, as we have seen, since frequency is reduced or some energy is less, and therefore that means if we know this relation between energy and frequency, E is equal to h nu. So for Stokes lines, it is E Stokes is equal to here it is nu 0 or nu minus this is delta nu, and here for this anti-Stokes it will be going to be h times nu plus delta nu. Nu is the original frequency of the radiation that is incident there, and therefore this is more, this is going to be more, and this is going to be less. So that's what invariably it is going to be stronger. So Stokes lines are invariably stronger than the anti-Stokes lines. So that is how the frequency is less means more energy, radiation is more energetic. Frequency is more means the radiation is less energetic. In that sense, Stokes lines are stronger than the anti-Stokes lines, or every time it is stronger than this anti-Stokes lines, and therefore question number 9 is the correct answer. It is invariably stronger. Or this question also can be asked in the different way. Anti-Stokes lines are dash dash than Stokes lines, so it is generally fainter. So anti-Stokes lines will be generally fainter than this Stokes lines, or Stokes lines are invariably stronger than this anti-Stokes line. So one can generate 2 questions or 3 questions from this particular simple statement as given in example or question number 9. Now question number 10. Raman lines are dash dash in gases, liquids and crystal, while in amorphous substance. Okay, lines are, now this is what we use transparent medium, either gas or liquid or sometimes crystals. So whatever Raman lines observed in that case, they are found to be somewhat narrow, whereas it is found to be somewhat broad and diffuse in case of amorphous substance. So like water or air or anything like this, transparent medium, etc., gas, liquid or solid, the Raman lines are found to be very, very sharp here. Whereas in this case of this amorphous substance, there are several different powder substance, amorphous substance. In this case, the lines observed here are diffuse one. Okay, so now that not broad, they are broad, and as well as they are diffused. That is because of the different molecular structures inside this particular amorphous substance. Whereas here in this type of air or this particular water or some substances, crystal structures, the structures are well defined, and therefore the spectrum which is obtained, the Raman spectroscopy, shows that the lines observed here are clear, that is narrow, and they are sharp and they are energetic, or this bright one. It is not the case here in this type of amorphous substance. Here it is broad and diffuse is found to be sometimes. So that is how this is the difference between the Raman scattering in case of crystals or gases or liquids, and in case of the amorphous substances. That also can be understood very easily on the basis of either classical theory or the quantum theory of the Raman effect. Question number 11. Width of the Raman line dash dash with increase in temperature. Now what happens to it? What happens to the temperature, and whether what happens to this width of the spectral line? Naturally, since this is a molecular phenomenon, okay, so it is a molecular phenomenon. That means molecules of the substance get excited and de-excited, and as this temperature increases, the vibrational motion or vibrational state of motion of that particular molecules goes on increasing. So there is a shifting, there is a change in the energy levels or vibrational energy levels, and thereby this causes the spectral lines going to be, that means otherwise at very low temperature, whatever Raman lines I am supposed to get, these are the Raman lines at very low temperature, some plus T is equal to 0. If T is made large in this case, if these Raman lines are observed, now their width is found to be increased, and this is because of this temperature effect. That means as temperature increases, width of the Raman line also increases, because this is a molecular phenomenon. This is not an atomic phenomenon. Since it's a molecular phenomenon, there is a change in the vibrational energy levels of the molecules, and this gives rise to a broadening of this Raman lines or Raman scattering lines, spectrum, and therefore this width of Raman line increases with increase in the temperature. So that is what the effect of temperature on the spectrum or the Raman line, that can be shown in this single statement as shown by this question number 11. Then question 12, Raman scattering radiation is dash dash. Either option, there are 4 options: partially polarized, completely polarized, not polarized, and option D is none of this. So this is again a theoretical. There is no complete polarization, there is a partial polarization. So partial means sometimes there is a plain polarization is like that, some part of that radiation get polarized, some part of radiation doesn't get polarized. So partial polarization is observed usually in the Raman scattering, but that also requires a lot of experimental setup for that, measuring its polarization and all these things. So complete polarization is not possible as what we see in the optical case, but here in the Raman scattering the partial polarization is observed. So that is again a theory question, conceptual question we can understand here. Question number 13, Raman spectroscopy offers a new method of studying crystals which is dash dash to X-ray diffraction. Now X-ray diffraction is one of the important tool we have seen earlier in X-ray diffraction pattern or X-ray spectroscopy. This tool is one of the tool that gives you internal, or that makes you understand the internal structure of certain crystals. Now this Raman spectroscopy, whether it helps, supports this particular X-ray spectroscopy, doesn't support this spectroscopy, or the result of this X-ray diffraction and this Raman spectroscopic diffraction, these results are supporting each other, not supporting each other, whether they are contradicting each other, that is to be answered here. Therefore option A is complementary, option B is non-complementary, option C is it is altogether different, that means and option D is contradictory. So out of this, C and D are same options, altogether different or contradictory. These are not applicable. So this particular Raman spectroscopy is complementary to this X-ray spectroscopy or X-ray diffraction. So additional details of the structure, additional details of crystal structure can be studied. Structure can be studied using this Raman spectroscopy, and that's why it supports, it complements, it enhances our understanding of the crystal structure, and that's why it is said to be complementary. That's what Raman spectroscopy offers, a new method of studying crystals which is complementary to the X-ray diffraction. So it adds, it doesn't show that X-ray diffraction is wrong or it gives you something different result. It is not that. It along with that, its internal structure, some other properties of this crystal structure can be studied into all details, and that's why it complements to this X-ray diffraction. That's why question number 13, correct option is E. Now question 14, Raman spectroscopy has been applied in the field in the study of some aspects of nuclear physics, such as, okay, so this Raman spectroscopy has been, these are the applications of Raman spectroscopy. So it verifies spin, it verifies the statistics of that particular sample or material whatever been given, isotopic constitution of the nucleus, so isotopic properties of the nucleus, that also can be studied, and thus all these 3 properties can be studied with the help of Raman spectroscopy. That's why correct option of this is D. So these are all applications of Raman spectroscopy, or nuclear applications of Raman spectroscopy in nuclear physics. Along with that, there are several applications other applications, we will find that lot many applications. Out of that, these 3 applications are found to be important. Okay, so these are the applications in the nuclear physics. Along with that, it has large many applications in chemistry, it has applications in biology and other branches of physics. This Raman spectroscopy plays a very important role. Of course, we are not going to go into all the details of these applications, but from our syllabus or the textbook point of view, these are the important applications of Raman spectroscopy in the nuclear physics. Whereas question number 15, the Raman effect has great value in organic. In the chemistry, special chemistry is organic chemistry, to determine option A, presence or absence of linkages of them in a molecule, whether there is some linkage in the molecules or not, that can be tested. So identifying impurities of certain types. So sometimes in certain organic chemicals, identification of impurities is very difficult by chemical processes, but physically that can be done very easily and simply by using this technique of Raman effect. So that is also one of the very important application. And option C is various chemical effects like strength of chemical bond, that also can be verified or studied using this Raman effect. Therefore all these are the applications of Raman effect in this organic chemistry. Therefore question number 15, correct answer is D, that is all of these applications of the Raman effect in the organic chemistry. So in our textbook we have been given Raman effect and its applications in the biology too, so you can go for that later on. Now that is our question 16. In biology, Raman effect is useful in the study of. So this is again all the applications I have listed one by one. A, structural and conformational changes and denaturation of macromolecules like protein and carbohydrates. So study of that can be done here. It is also used to study structural and conformational aspects of lipids, biological membrane and lipid protein complex. So that biological structure of these type of molecules also can be studied. So both the statements are true, and option D is neither of the statements are true. Yes, both the statements are true, and therefore our correct option of this question number 16 is C. You will find that that is how this particular Raman spectroscopy has many applications, not only in physics but in chemistry as well as in biology as well as some other branches of the other scientific branches, scientific instruments. This Raman spectroscopy plays a very important role. Now question number 17, the elastic scattering of photons is called as, okay, this is what elastic scattering of proton is called as atmospheric scattering, Rayleigh scattering, conserved scattering and the Raman scattering. So here this is what the scattering here, it is an elastic scattering, and that's why this is also called as the Raman scattering. So question number 17, D is the correct answer. Elastic scattering of photon is called as the Raman scattering. Then question number 18, the Raman scattering is the inelastic scattering of proton of, this is the earlier statement we have correct, it was not correct. It is not Raman scattering, but this is the Rayleigh scattering. Okay, so this elastic scattering of photon is called as the Rayleigh scattering. That is what already we have seen its properties, and therefore this is in Raman scattering, it is an inelastic scattering. The Raman scattering is the inelastic scattering of a photon by a molecule. In inelastic scattering, the the is not conserved. So total energy, momentum, kinetic energy or electronic energy, so there is no question of this electronic energy, but the kinetic energy of these molecules of the transparent substance, that plays a very important role, and that energy changes. So in inelastic scattering, some amount of energy is lost in the process, and that's why this is an inelastic scattering, and therefore Raman scattering is the inelastic scattering of a photon by a molecule. In inelastic scattering, the kinetic energy is not conserved. Total energy is always conserved in any of the process, but kinetic energy in this process is not conserved, and that's why we get this Raman scattering as shown in earlier questions. Question number 19. In Raman spectroscopy, the radiation lies in the electromagnetic spectrum. Out of that, whether it's a microwave region, whether it is visible region, whether it is ultraviolet region or it is X-ray region. So in this electromagnetic spectrum already we have seen, this is gamma radiations, these are X-rays, this is ultraviolet, here it is visible and infrared. So this entire band is said to be visible and infrared. Okay, and apart from that, then this is microwaves, radio waves, and so many things here. So this is the part, actually this is the part here where this Raman spectrum plays a very important role. So it is on the boundary of visible as well as infrared. So out of this is so infrared is also a part of sub part of this visible radiations. That's why question number 19B is the correct option. The Raman spectroscopy, the radiation lies in the visible region. Okay, neither microwave region, nor ultraviolet region, nor X-ray region, or not gamma region, or anywhere. So this is one special type of spectroscopy which is different than the whatever things we have learned in earlier chapters. Now question number 20. The Raman spectrum is said to be consist of Stokes lines. Okay, Stokes lines, as we have already seen, this is what we have written expression, nu is equal to nu 0 minus delta nu. So this minus delta nu, that means if this change in the frequency is less than 0, then the line is called as Stokes line. If the change in the frequency is greater than 0, then this is anti-Stokes. So you'll find that means how many number of ways one can ask questions on the Stokes lines, anti-Stokes lines, either in terms of frequency, in terms of change in the frequency, whether in terms of their location, in terms of their symmetry, etc. Several type of questions are asked, and therefore correct answer of this question number 20 is B. It is delta nu is less than 0, or if it is negative, then that particular line is called as the Stokes line. So the Raman spectrum is said to consist of Stokes lines when this delta nu is less than 0 or it is negative, and D, option D, does not depend upon delta nu. This is not the case. So delta nu greater than 0, it is anti-Stokes lines. Delta nu is equal to 0 is the Stokes lines, and delta nu is equal to 0, this is your Rayleigh's line. So Rayleigh's anti-Stokes, sorry, this is Stokes and earlier is anti-Stokes. So we can understand this is again in terms of this question number 20. Last question, I think. The Raman lines are usually, okay, second last, Raman lines are usually weak, strong, curved, and blurry. So there is no question of blurry, no question of curved, no question of strong, because Rayleigh's lines are much stronger, and therefore these Raman lines are usually weak as compared to other types of lines, that is Rayleigh's lines are like that, and therefore question number 21 correct option is A, that is weak. Raman lines are usually weak or weaker as compared to any other. See, already we have seen just 0.01% of the incident radiation gets scattered in the form of Raman spectrum or Raman lines, that is Stokes lines or anti-Stokes lines, and therefore it is much weaker as compared to ordinary scattering or Rayleigh scattering and in total incident radiations and so on. And the last question, question number 22, which of the following lines are most intense? Stokes lines, Rayleigh scatter lines, then anti-Stokes lines, and all have same intensity. So naturally out of this, these Rayleigh scattered lines are more intense. The Stokes lines and anti-Stokes lines, they are very feeble, very weak, and that requires a specialized instruments to identify these type of scattering lines. With your ordinary spectrometry, it is not that easy to identify Stokes lines as well as anti-Stokes lines, and therefore these are the important concept based questions on this particular chapter. That is a Raman spectroscopy. Purposefully I have not designed, or we have not design any questions which are based upon some numerical problems, because this quantum theory as well as classical theory, all these things give you all the such type of problems are there, but to make the things more easy and comfortable for you, we have selected only theoretical and conceptual based questions. I hope you will also enjoy and like this particular video. So please share your comments as well as your suggestions or whatever your opinions about these type of videos. So in the last video we are going to come across the molecular spectroscopy, maybe one day or two. Till then let's take a break, and thank you for patience watching of this particular video on this Raman spectroscopy. Thank you once again.